This will be part B of problem 2 from the 2014 AP Calc AB exam. You've got this region R here, and in part B it says the region R is the base of a solid. So we have something that's sitting on this base. It has a flat base to it, and it's coming off the screen toward us. For the solid, each cross-section taken perpendicularly to the x-axis is an isosceles triangle with a leg, isosceles right triangle with a leg in R. Find the volume of the solid. So it says to cut down into the solid perpendicularly to the x-axis. So if I cut down into the solid like that and I remove that slice from the solid, what I end up looking at is an isosceles triangle that also happens to be a right triangle. So my best attempt at doing that would be this. Now this does have a little bit of thickness to it because it comes out of our three-dimensional solid, and so our thin slice of the solid would look something like this. Now if we were able to physically pick this up off the board, off the screen, and turn it and slide it back down into the gap in the solid from where it came, this flat edge right here is going to have to sit perfectly back down into the base of the solid. So what I just shaded on the cross section is going to correspond to this from out of the coordinate plane. Now, why is it important to make that connection? Well, if you can specify this dimension from in the coordinate plane, from this y value to this y value, that's also going to be the height of the left side of that triangle. And if you know that that's the height of that side of the triangle, since it's an isosceles triangle, that's also going to be the distance across the bottom here. So this dimension in the coordinate plane would be found by specifying a difference in y values. We'd take the bigger y value, which is at y equals 4 on that line, and then minus the smaller y value. The smaller y value is on the function f of x. So we'd have 4 minus f of x for the height on that edge of the triangle, and since it's isosceles, that would also be the dimension across the bottom. Now the area of the face of this triangle would be 1/2. If we call this the base and then this the height, since that's already serving as an altitude, since the triangle is a right triangle, we can get away with that. To find the volume of this one cross section, what we can do is we can restate the area of the face of the triangle, and that's going to be 1/2 base times height, whichever one you want to call the two, and that's the same quantity being multiplied by itself, so I'm just going to express that with an exponent, and then times the thickness. Well, the thickness of this is going to be some tiny difference in x values, this dimension from out of the coordinate plane, so that's going to be a delta x. This would be the volume of one cross section. We want to find the volume of the whole solid by adding together the volume of many of these cross sections, so we're going to use the integral as our tool to do that. So if we toss this into our integral is going to be done with respect to x. The x values that all slices range between within this region would be from this x value to this x value. Back in part A, we spoke about those intersections. It was 0, 4 and 2.3, 4. Those are intersections that you can find by graphing y equals 4 and graphing y equals the quartic function on your calculator. So the limits of integration would be 0 and 2.3. And if you want to do this integral on a calculator active section of a test, break out the calculator, have the calculator do the rest of the legwork for you. So you've done all the setup, and I have already typed this in. Just let me recall it here. So I grabbed out of the math menu the function integration feature, and I carefully typed in my integrand. I did obviously have to type in f of x in this form and not just calling it f of x, standard name. Be careful with grouping symbols there. I had to double check mine once or twice when I saw something weird happen initially. So just be really careful with your grouping symbols, and if you are and you evaluate, you end up with a volume of 1.737 cubic units for the solid that sits on that base.